In the last two tapes, we studied trig functions of some basic angles. In this tape, we'll use that information to solve some problems involving trigonometry and also some trig equations. Let's start with the following problem. How long should an escalator be if it is to make an angle of 30 degrees with the floor and carry people a vertical distance of 25 feet between floors. How long should an escalator be if it is to make an angle of 30 degrees with the floor and carry people a vertical distance of 25 feet between floors? Okay, let's try to draw a picture of what's going on here. Imagine we have some kind of a department store or whatever. Here is our first floor. And here is the second floor. And there's an escalator running between the first and the second floor. Okay, something like this. And the escalator makes an angle of 30 degrees with the first floor here. Okay, here is your escalator. Right? And it makes an angle of 30 degrees with the floor. We want to figure out the length of this escalator if it is to carry people a vertical distance of 25 feet between floors. In other words, to draw in here a vertical line, segment this distance between the first floor and the second floor is 25 feet from here to here. Here we have our escalator. We are looking for the length of the escalator. Let x represent the length of the escalator in feet. The length in feet of the escalator. Okay, and the escalator makes an angle of 30 degrees with the floor here, with the first floor. Okay, so we have a right triangle set up. We know this angle. We know the length of the side opposite this angle. And what we don't know is the hypotenuse of the triangle. It's a situation of knowing the length of the side opposite and wanting to find the hypotenuse. If you remember the mnemonic SOHCAHTOA, the sine of, in a right triangle, the sine of an angle is the length of the side opposite the angle divided by the length of the hypotenuse. The cosine of an angle is the length of the side adjacent to the angle divided by the length of the hypotenuse. The tangent of the angle is the length of the side opposite the angle divided by the length of the side adjacent to the angle. Okay, if we know the side opposite and we want to find the hypotenuse, this looks like a setup for sine, since the sine of an angle is the opposite side over the hypotenuse. Okay, so we write down that the sine of 30 degrees is 25 over x. The sine of 30 degrees is opposite over hypotenuse, 25 over x. The sine of 30 degrees is 25 over x. The idea is to get the unknown, in this case x, as part of some sort of an equation. And we have logical choice here is to use the sine function. The sine of 30 degrees is opposite over hypotenuse, 25 over x. The only thing we don't know is x, and we can solve for x. Now, in this particular case, 30 degrees, I used a basic angle, one whose sine you're supposed to know. If not, I suggest you go back to one of the previous tapes when we studied trig functions of basic first quadrant angles. Okay, well, the sine of 30 degrees happens to be a half. By the way, if the escalator had made an angle with the floor that was not a basic angle, say 33 degrees or 35 degrees or whatever, you could always use a calculator or a table of values of trig functions to figure out the sine of that angle. Okay, you would then write that down, equal to 25 over x. And here we have a very simple equation to solve. It involves fractions, but we can multiply both sides of the equation by the LCD. In this case, it's just 2x. Multiply both sides of the equation by 2x. On the left side, okay, we get 2x times 1/2. The 2's cancel, we get x equals. And on the right side, the x's cancel, we get 25 times 2, which is 50. By the way, since this is in the form one fraction equals another fraction, we could have also solved this by cross-multiplying. We would have gotten 1 times x is equal to 2 times 25. Also, x is equal to 50. Okay, so the length of the escalator is 50 feet. Okay, we're looking for the length of the escalator here, and x is the length. And the answer to the problem, the escalator should be 50 feet long. Okay, let's try another example. I'm going to give you a right triangle. Let's call it right triangle RST. RST with a right angle at S. I'm going to tell you that angle R is 45 degrees and that the hypotenuse, the length of side RT, is 100 units. And I'm going to ask you for two things. One, find the length of side RS, and two, find the area of right triangle RST. I want the length of side RS and then also the area of right triangle RST. Okay? Now, let's denote the length of side RS by x. X will represent the length of this side. All right, we have a situation here where we know an angle. We know the side, we're looking for the side adjacent to the angle, and we know the hypotenuse. Okay? Now, if you know the hypotenuse and you want to find the side adjacent, this is a setup for the cosine function. Okay? Remembering SOHCAHTOA again. In the previous problem, we used the sine function because we knew the side opposite and we wanted to find the hypotenuse. Let's just go back and look at the last problem for a second. In the last problem, we knew an angle, we knew the side opposite, and we wanted to find the hypotenuse. So naturally we used sine. The sine of 30 degrees was the opposite over the hypotenuse 25 over x. However, now, it's a slightly different problem. We want to find the side adjacent to this angle. We know the angle and we know the hypotenuse. So instead of using sine, we're going to use cosine. Cosine relates the adjacent side and the hypotenuse. The cosine of 45 degrees is equal to adjacent over hypotenuse x over 100. Multiplying both sides here by 100, we get that 100 times the cosine of 45 degrees is equal to x. Now, the cosine of 45 degrees, this is also 45 degrees is another one of our basic angles. The cosine of 45 degrees is the square root of 2 over 2. So we get that x, the length of side, RS, is 100 times the square root of 2 over 2, or 50 times the square root of 2 units. This is the length of side RS. Okay, that answers problem 1. Now on to problem 2 here. We want to find the area of the right triangle. Well, in any triangle, we know that the area is 1/2 base times height. Okay, it's particularly easy to find the area of a right triangle because you could consider, say, one leg to be the base and the other leg to be the height, because these sides are perpendicular to each other. Okay, instead of 1/2 base times height in a right triangle, we just say 1/2 the product of the legs. So the area of this triangle is 1/2 the length of RS times the length of ST. Let's denote the length of ST by Y for the moment. Okay, so the area is going to be 1/2 XY. 1/2 the product of the legs. Now, so we know X, we would first have to find Y. Now there are two ways to go about this. One way would be to say, look, I need to find the side opposite 45 degrees. I know the hypotenuse. I can work it out. The sine of 45 degrees is Y over 100. Y comes out equal to 100 times the sine of 45 degrees, and work it out that way. Another way is to say, if this is 45 degrees and this is 90 degrees because it's a right triangle, and there's only 180 degrees in all three angles of any triangle, since they have to add up to 180, and we have 90 and 45, this must also be a 45-degree angle. 45 and 45, 90 and 90, giving me 180. This would therefore be an isosceles right triangle, and X would be equal to Y. Okay, so we have 1/2 X times X. Y is equal to X because it is an isosceles right triangle. And if you worked it out using sine, you would get the same answer for Y that you got for X. Okay, so 1/2 X, which we just found out to be 50 the square root of 2, times 50 the square root of 2. Let's see what we have. 50 times 50, that's 2,500. The square root of 2 times the square root of 2, that's 2. But then you have the 1/2, so the 2's cancel. Okay, so all you're left with is that the area is 2,500 square units. Let's go over that again. 1/2 X times Y, which is 1/2 X times X. Now, the 50 times the 50 gives you the 2,500. The square root of 2 times the square root of 2, that's 2. When multiplied by the 1/2, that gives you 1. So they cancel. So you just get 2,500 square units for the area of right triangle RST. Okay, let's spend some time trying to solve some simple trig equations now. That is, equations involving the trig functions. Let's start with the following one. In all of the problems that I give you, I want you to solve for X, where X is some angle between, and I want all solutions between 0 and 360 degrees. Or if you were using radian measure, solutions between 0 and 2 pi. Most people solve the equations in degrees, and then if they want to, they can transform their answers into radian measure. In calculus, you will have reason to solve trig equations, get the answers, say, in degrees, and then transform into radians, okay? Because the radian measure must be used in calculus for reasons that will be explained in your calculus classes. Okay, so we're looking to solve trig equations for all angles between 0 and 360 degrees, which work. Let's start with the following problem. The square root of 8 sine x plus 12 equals 4. And for the most part, we're going to be using the same tricks that we used in dealing with equations that did not involve trigonometry. For example, in a radical equation of this form, the first thing to do would be to square both sides and to eliminate the radical. Okay, this has not changed. Just because we're dealing with trig equations, the procedure is still basically the same. Okay, square root of 8 sine x plus 12 equals 4. We square both sides to start solving this. 8 sine x plus 12. When you square the left side, of course, the radical drops out, squares out. And when you square the right side, you get 16. Okay? 8 sine x equals, now subtracting 12 from both sides, 8 sine x is equal to 4. We subtract 12 from both sides, giving us 8 sine x is equal to 4. Now we would like to solve for x, but first we're going to have to solve for sine x and then work back. Okay? So we want to solve right now for sine x, dividing both sides by 8. Sine x is equal to 4/8 or 1/2. Now, in the last few tapes, we were working slightly differently. I was giving you angles, and basic angles. We were finding trig functions of these basic angles. Here, slightly different procedure. We know what the sine is. We want to figure out what the angle is. Okay, now, if this were not the sine of a basic angle, okay, you could write this out in decimal form, look in a table of values, figure out what x had to be. But this happens to be one of those angles whose sine you're supposed to know. The sine of 30 degrees, if you remember from an earlier tape, and if not, I suggest you review the earlier tapes on basic angles. The sine of 30 degrees is 1/2. Now that's one solution to this equation, but it's not the only one between 0 and 360 degrees. Now I realize that the trig functions are periodic, so after 360 degrees there are going to be more solutions. Okay, we have set up something like this. The sine function between 0 and 2 pi radians looks something like this, but then it begins repeating, okay, and so on, in this way also. We want the sine of an angle to be 1/2. Okay, let's say if this is 1 at pi over 2 radians, or 90 degrees, then 1/2 is about here. This is like the 30 degrees, or the pi over 6 radians. There is another solution here. Okay, once you're past 360 degrees or 2 pi radians, there are going to be other solutions. We're only interested in those solutions between 0 and 360 degrees. But we can see that even between 0 and 360 degrees, there's going to be more than one solution. Okay, now if you remember from the last tape, we were discussing second, third, and fourth quadrant angles, and how you could, instead of finding trig functions for these angles, deal with corresponding acute reference angles. Okay, you found the corresponding acute reference angle, and then you worked with the trig function of that angle instead. Here it's slightly different. We know sort of like the reference angle. We want to figure out the corresponding angle in the second, third, and fourth quadrants. If you remember, we were measuring our reference angles off the horizontal or off the x-axis. Okay, this in conjunction with the fact that we know in which quadrants the various trig functions are positive and where they're negative. This is, say, quadrant 1, quadrant 2, quadrant 3, and quadrant 4. You'll remember the mnemonic I gave you in the last tape. All students take calculus. This meant that in the first quadrant, all the trig functions were positive. In the second, sine and its reciprocal, which is cosecant. Okay, if sine is positive, 1 over sine of something is going to be positive. In the third, tangent was positive and its reciprocal, which is cotangent. And in the fourth quadrant, cosine was positive and its reciprocal, which is secant. All students take calculus. All trig functions are positive in the first quadrant. Sine and its reciprocal in the second are positive. They're the only ones that are. Tangent and its reciprocal are positive in the third quadrant. Cosine and its reciprocal are positive in the fourth quadrant. Here we have the sine of an angle is 1/2. It is positive. We know that the sine is positive only in the first and the second quadrants. Okay, so we have 30 degrees as one answer. The other answer will be in the second quadrant, 30 degrees off the horizontal. Whichever, in other words, part of the x-axis happens to be closer. 30 degrees off the horizontal here gave us 30 degrees. 30 degrees off the horizontal here, this is 180 degrees. 30 degrees this way into the second quadrant gives us 150 degrees as the other answer to this problem. Okay? If one were trying to find the sine of 150 degrees, we would use the corresponding acute reference angle, which is the angle between the terminal side of 150 degrees and the nearest part of the x-axis, which is the negative x-axis here, and that, of course, would be 30 degrees. So 30 degrees goes with 150 degrees. Both of these angles have sine of 1/2. Okay, and they're the only answers between 0 and 360 degrees. If you had reason to give the answers in radian measure instead, then you would write x equals, and you would transform these degree measures into radian measure by multiplying by pi over 180 degrees. If you multiply by pi over 180 degrees, 30 into 180 goes 6 times. We get pi over 6 for 30 degrees. And here, multiplying by pi over 180 degrees, we would get 5 pi over 6 for the other answer. So we have two answers to this problem, either 30 degrees and 150 degrees, or pi over 6 and 5 pi over 6 radians. Those are the only answers between 0 and 360 degrees, or 0 and 2 pi radians. So there are other solutions if you would not restrict yourself to being, say, between 0 and 360 degrees. Okay, let's try another trig equation. This time we'll work with 1 plus tan x over 8 equals 7 minus 2 tan x over 20. Okay, the last time we worked with a radical equation. Now we have a fractional equation. And once again, the rules for working with fractional equations still apply. Don't let the trigonometry upset you. Okay? To handle a problem like this, we would try to get rid of fractions first. We would accomplish that by multiplying both sides of the equation by the LCD, which is the lowest common denominator for 20 and 8. Looking for the smallest number that 20 and 8 both divide evenly into, and that would be 40. So I'm going to multiply both sides of this equation by 40 to clear fractions. You could also solve this equation, since it's just one fraction equal to another, by cross-multiplying, but it wouldn't be any easier. In fact, you get a slightly more complicated equation to work with. 8 into 40 goes 5 times, so you have 5 times 1 plus tan x equals 20 into 40 goes twice, so 2 times 7 minus 2 tan x. 8 into 40 goes 5. 5 times 1 plus tan x equals 20 into 40 goes twice. 2 times 7 minus 2 tan x. Now on the left, let's distribute the 5 through the parentheses. Don't forget, it's 5 times the 1 and then 5 times the tan x equals 2 times 7, that's 14, minus 4 tan x. Same distributive law that you were using before, you still use here. Okay, the unknown now is x, but first it's going to be tan x. First we'll solve for tan x, and then work backwards and figure out x. So let's try to get all the terms of tan x on one side, everything else on the other. I can add 4 tan x to both sides of this equation. Giving 5 plus 9 tan x equals 14. And then subtract 5 from both sides of the equation, giving 9 tan x equals 9. Divide both sides of the equation by 9, giving us tangent x equals 1. And we're trying to figure out what x is. Okay? We multiplied both sides of the equation by the LCD, cleared fractions, distributed the numbers outside the parentheses through the parentheses, solved for tan x. We got tan x is equal to 1. And now we are looking for x. Okay, now you have to start off by knowing that the tangent of 45 degrees is 1. As I said, if you're weak on your basic angles, I suggest you look at the earlier trig tape basic angles in the first quadrant. Okay, 45 degrees is one answer. Of course, if you have a table, you could always look in that. The tangent of 45 degrees is 1. We're looking to see are there any other answers between 0 and 360 degrees. Let's go back and look at this again. tangent is positive in the first quadrant. All the trig functions are positive in the first quadrant. It's positive again in the third quadrant. So we are looking for an angle that corresponds to 45 degrees in the third quadrant. The angle whose acute reference angle would be 45 degrees. It would be 45 degrees off the horizontal in the third quadrant. If this is 180, it would be 180 plus 45 degrees for 225 degrees as our other answer. It's 45 degrees off the horizontal into the third quadrant. 180 plus 45, 225 degrees. And if you want to write the answers in radian measure instead, you can multiply by pi over 180 degrees to get pi over 4, which is equivalent to an angle whose degree measure is 45. And here, multiplying by pi over 180 degrees, we get 5 pi over 4. Okay. Once again, two answers between 0 and 360 degrees. Let's try one last problem on this tape. We've done a radical equation, a fractional equation. Let's do now a quadratic equation involving trigonometry. Two cos squared x plus sine x equals 1. Okay, now, slight catch here. This is the first time I'm introducing a new way of working with an equation. The other ones, the radical equations, the fractional equations, we handled the same way we handled the equations that did not involve trig. Here, I'm going to make a slight request from you. If you're working with a trig equation, let's see if we can work with only one trig function in that equation. It's easier for you if there's only one trig function involved. Here we have cosine and sine together in the same equation. It would be easier if there were just cosines or just sines in this equation. Okay, now, the question is, which is it easier to get rid of? Is it easier to make cosine into sine or sine into cosine? Remember that we have a relationship which links sine and cosine. The basic trig identity, sine squared x plus cos squared x equals 1. This is the Pythagorean identity, one of the most basic of the trig identities. Okay, from this I can see that it'll be easier for me to change cos squared into something involving sine. Cos squared x is 1 minus sine squared x. If I wanted to go the other way and change sine into cosine, here I would have sine squared x is 1 minus cos squared x, but I need sine, so I'd have to take square roots, and I'd be bringing radicals into an equation that didn't involve them. So it's certainly easier, since it involves cos squared here, to try to get everything in terms of sine. Okay, cos squared x is 1 minus sine squared x. Remembering that, I'll rewrite the equation as 2 cos squared x plus sine x equals 1 as 2 times 1 minus sine squared x plus sine x equals 1. Using the fact that if sine squared x plus cos squared x equals 1, then cos squared x must be equal to 1 minus sine squared x. And that's what I've replaced it by. I'm replacing cos squared x by 1 minus sine squared x. So my equation only involves sine now. Cos squared x is 1 minus sine squared x, since sine squared x plus cos squared x equals 1. Okay, let's try to solve this. Distributing the 2, we have 2 minus 2 sine squared x plus sine x equals 1. All right. Let's try to bring everything over to the left side. Subtracting 1 from both sides of the equation, I get 1 minus 2 sine squared x plus sine x equals 0. I subtracted 1 from both sides of the equation. 1 minus 1 gave me 0. Here, taking away 1 from the 2 gave me 1. Let me rearrange the terms. Let's make it minus 2 sine squared x. Put the quadratic term first, then the first degree term, sine x, then plus 1 equals 0. Minus 2 sine squared x plus sine x plus 1 equals 0. Minus, let me just rewrite it here, minus 2 sine squared x plus sine x plus 1 equals 0. Some people have trouble dealing with this equation because it involves sine x. Let's just temporarily pretend that sine x, that whole business, was just replaced by the letter s. Then you would have minus 2s squared plus s plus 1 equals 0. This looks a little bit more like a quadratic equation. All I've done is let sine x just represented by the letter s. Sine x is equal to s. Okay, if this were your quadratic equation that you wanted to solve, you probably would try factoring, but before you would do that, you would know that it's usually easier to factor if the lead coefficient is equal to plus 1. So let's multiply both sides of the equation by minus 1 to change all the signs. Okay, minus 1 times minus 2s squared, that gives you plus 2s squared. Then minus s minus 1 equals 0. 0 times minus 1 is still 0. And this is solved very simply by factoring. 2s and s would be the only way to make the 2s squared. If we put a plus 1 here and a minus 1 here, let's check that by FOIL. 2s squared minus 2s plus 1s, that's minus s minus 1 equals 0. We've factored this very simply. We then say the product of two numbers is equal to 0, then either the first number is 0 or the second one is equal to 0. We set each factor equal to 0. We get here 2s is equal to minus 1. S is minus 1/2. Here s equals 1. By the way, remember that I just put s in to help you, so you shouldn't have to carry around the sine x. What we really have found is that sine x is minus 1/2. Sine x equals 1. It's a quadratic, and there are two possible solutions, each one of which now is going to give rise to different x values. Okay, if you find this convenient, okay, feel free to use this idea of replacing, say, once you get it all in terms of one trig function, replacing that trig function, say, just by the first letter until you've solved the quadratic equation. Okay. The one on the right is the easiest to solve. Sine of x is equal to 1. That happens only once between 0 and 360 degrees. That happens only at 90 degrees. The sine of 90 degrees is equal to 1. X is equal to 90 degrees, or pi over 2 radians. That's one solution. Now, let's see over here what we get in the way of solutions. Sine of x is equal to minus 1/2. Let me go over to the side for a second. Sine of x is equal to minus 1/2. Remember, all students take calculus. All trig functions are positive here. Sine is positive here. Okay, sine is negative in the third and the fourth quadrants. The first thing we do is we ignore the minus 1/2, and we say if it had been plus 1/2, we know the angle would have been 30 degrees. Okay, the basic reference angle to use here is 30 degrees because the sine of 30 degrees is 1/2. However, we want the sine to be minus 1/2. So we are looking for the angles that correspond to 30 degrees, but in the third and the fourth quadrants where sine is negative. The sine of 30 degrees is plus 1/2. We want the sine to be minus 1/2. We start with the 30 degrees, but we say it can't be 30 degrees or 150 degrees. Can't be in the first or the second quadrant because sine is positive there. We're looking for the corresponding angles in the third and the fourth quadrant. That is, the angles that are 30 degrees off the horizontal into the third and into the fourth quadrant. So, in the third quadrant here, we have 180 plus 30, or 210 degrees. And in the fourth quadrant, 30 degrees off the horizontal, this is, say, 360 degrees. 30 degrees less than that would be 330 degrees. Okay, so we get 180 degrees plus 30 in here, 360 minus 30 in here. The angles which correspond to 30 degrees in the third and the fourth quadrant where sine is negative. So let me put those answers down here. X is 210 degrees and 330 degrees. And if you want, you can transform them into radian measure as well. 210 degrees multiplying by pi over 180 degrees gives you 7 pi over 6. And 330 degrees gives you 11 pi over 6 radians. So there were 2 answers from this left factor and 1 answer arising from the right factor. Between 0 and 360 degrees, the solutions to this equation are 90 degrees, 210 degrees, and 330 degrees. Or pi over 2 radians, 7 pi over 6 radians, and 11 pi over 6 radians. And that brings us to the end of the tape.